Hi, I'm Amin, and this is a video presentation for my Physics 102 lab project. The purpose of my project was to measure the strength of the geomagnetic field using a current running through a wire. Electric currents create magnetic fields as explained by the Biot's law, and using this law, we can drive the strength of the magnetic field created by the current at the center of the loop. Since compasses point in the direction of the total magnetic field, we will then measure the angle of deflection to find the ratio between the geomagnetic field and the magnetic field created by the current. In the lab, I used a circle of wire made out of copper and noted down its characteristics such as the number of loops and the diameter. I also measured the resistance of this wire for future reference. Then, I connected this wire in series with a resistor and a DC power supply. I held the compass such that it would point perpendicular to the axis of the wire and set the power supply to 5 volts. As can be seen, this caused a deflection in the compass needle. I photographed the compass to be able to make a precise angle measurement, which I will use in my calculations. I then repeated the steps for 10, 15, 20, and 25 volts. After the lab, I measured the angle of deflection for the different voltage levels. I also calculated the current running through the wire using Ohm's law. Since we can relate the angle of deflection to the ratio between the two magnetic fields, we can use this information to calculate the strength of the geomagnetic field. I calculated these values for different voltage levels and plotted them on a graph as shown. As can be seen, our data varied from about 35 to 40 microtesla's, though we had large error bars that were caused by the measurement errors in the radius and the angle of deflection. Since we expect the geomagnetic field to be independent of the voltage, we fit our data to a polynomial of degree 0, a constant. Our best fit was 37.2 microtesla's, which seems reasonable as the strength of the geomagnetic field varies between 22 and 67 microtesla's on the Earth's surface. In my experiment, there were several sources of error, the principal of which was my measurement devices. These measurements include angles, resistance, voltage, and diameter. The error caused by the diameter measurement was especially large since our diameter was quite small, so it might have been beneficial to use a device like a micrometer rather than a ruler to obtain better results. I ignored the dimensions of the compass and assumed that the magnetic field was roughly constant in the region we are investigating, which is another source of error. I also ignored the potential effects of external fields that might exist in the lab. However, these last two error sources are likely to be minor, especially compared to our measurement errors. Overall, we achieved a result that seems feasible and which aligns with our expectations based on the theory we know. In a potential repeat experiment, we may consider using more sensitive measurement devices or constructing a Helmholtz coil to mitigate our error sources and obtain more precise results.